Welcome. I am just getting connected for live stream today. I wanted to talk about constraints and generalized forces and also generalized coordinates. Let me double check this. Welcome. I am just getting connected. We are up and running. Cool. All right, so constraints, generalized forces, generalized coordinates, all of this doesn't make a lot of sense right now as we're just getting started with Lagrange and kind of dynamics, equations of motion. So it helps to look at some specific examples and then try to build the general idea from there. So let's start off with something from an example from the this is the Wells Lagrange dynamic. And it's figure 4.1, example 4.6. If you're interested in kind of like going through and seeing where all this came from. So we have one big pulley. And that's attached to our weight of M1. This comes down, and then we have another pulley that attaches M2 and M3. There we go. Let's make that one a little longer. And it helps to kind of start off with pulleys because they're all one-dimensional motion, and then the constraints are just are they moving up or down as something else moves up or down. And we can put a floor down here if we want. The floor isn't really affecting the motion of the system, but it does create not a constraint. It's not creating constraint on motion, but it is creating like a bound on the motion. Okay. So when I look at this system, first question is, how many degrees of freedom do I have? And what is a degree of freedom? The number of independent properties needed to define a system. This is why it helps to start off with a concrete example rather than the general statement and try to apply it. Is that this is a very vague statement that the number of independent properties, that the minimum number of independent properties needed to define the system define its degrees of freedom. So in this specific case, I would say there are three moving parts. So 3 parts. So 3 things that can only move up and down. So here's 1, there's 2, there's 3. Do I want to start with that? So I have these 3 moving things, and I'm ignoring the pulleys for now. And we can come back to that if we want to try it. So let's say I take M1 and I pull it down, what happens to M2 and M3? Well, M2 and M3 both have to move up, but because this pulley moves up, so both of them are going to move up. Okay? So there's some connection there. What happens if I say M1 can't move? Can M2 and M3 move? And the answer there is yes, they can both move, but not independently. So if M1 can't move, then if this one moves down, M3 has to move up. So by removing one, a constraint like this is a -1 on my degrees of freedom. I only have 1 degree of freedom left. And this is kind of using an intuition approach. So intuition says 2 degrees of freedom. If I have 2 degrees of freedom, then I only need 2 things to describe where this thing is. So let's say I know that this is 1 meter, and I know this is 1/2 meter. Then the length of this core, the length of these 2 tensions are fixed, and M3 has to be defined as something. So if I say that this is L1 and this is L2, then I can work my way around that chord and figure out that position 3 has to be a function of those other 2. I could have chosen x3 as my independent coordinate, or I could have chosen... The one thing that I can't do is say I can't use 2 dependent coordinates. So I can't say that this is 1 meter and then my other coordinate is that this is 2 meters, and then try to figure out the position of mass 2 based on just 2 different positions of mass 1. All right, so now let's look at something with the Grubler count. So take this. So Grubler count is a general way of trying to figure out what the degrees of freedom are for a system. And this is going to factor in everything that's moving. And everything is a rigid body. So in this case, because it's 2 dimensions, we're saying that there are 3 degrees of freedom. It's X, it's Y, and some kind of orientation. So when I do this, I have body 1, body 2, body 3, pulley 1, let's call it P1, pulley 2. And all five of these things are moving. So I have 5 times 3 equals 15 degrees of freedom. But I have a hinge on pulley 1. So a hinge creates two constraints that pulley 1 can't move x and y, like x and y are fixed. Oh, didn't mean to do that. Then I have a cord connecting M1 to pulley 1. So cord -1, because it's limiting that L1 has to be a constant. Then there's another cord, so another -1. And then cord 1, cord 2. Then we also have a constraint that mass 1, mass 2, and mass 3, they're only moving up and down. And same with pulley 2, it's only moving up and down. So we have M1, M2, M3, and pulley 2. Xi is constant. Maybe I should move that one over because that one's just describing my constraint. So 1, 2, 3, and 4 where x, well, I guess I'm saying x, but I'm saying like this. If this is my x displacement, maybe left, right. Do we want to leave it as x? We could call it x. Xi is constant, and then we'll use this global coordinate system like this. So xi is constant, so -4. So now we're down to 15, 13, 12, 11, down to 7. So then what else is going on here, right? Well, we also have the constraint that if M1 moves up, theta has to change. So this, like the orientation of that pulley, so there's a y1 to theta pulley 1 -1, and then there's a y2 to theta pulley 2, that if y2 moves up and down, then that pulley has to move up and has to rotate. And what are we down to now? 2, 3, 4, 8, 9, 10. So we're down to 5 degrees of freedom already. So what are the other constraints that we have here for our Grubler count? Because I think there's still only 2 degrees of freedom. And we took care of it's only moving up and down for all of these, that our x positions are all constant. And then we also have that y1 dot is a negative y3 dot, or sorry, y2. So that's another -1, because if y2, if the only thing that changes is that this moves up, then this one has to move down. And then same thing here, that if this one moves up, pulley 2 has to move down. And where are we at now? 2, 6, 8, 9, 10, 11, 12. So it's 3 degrees of freedom. Oh, and the last part is we only have that we're not rotating M1, M2, and M3, that theta 1, 2, and 3 are all constant. Did I add up too many? I might have done same thing twice, so let's double check. 2, 4, 8, 9, 10, 11, 12, 15. So it shouldn't be 15. So I did something wrong. Oh, the chord. I double counted the chords. Sorry about that. Because these two constraints are already counted up here. Because I just said that the chords exist. So I can't double count the constraint. Well, technically I can, but like sometimes you have multiple constraints that are doing the same thing, and then your Grubler count might be negative, but in this case, I don't. I just double counted it. So overall, I have 2 degrees of freedom. I find that it helps to do both ways, where you do both an intuitive approach of like, if I hold one thing constant, then what can the rest of the system do? And then also do this approach where you look at, okay, what is every possible thing moving in this system? Multiply that by 3, at least for 2 degree freedom. If you have a three-dimensional thing, then it has 6 degrees because you have X, Y, Z, and all the orientations. Okay, cool. So we have 2 degrees of freedom. When we figure out how many degrees of freedom we have, then the next step is defining what our generalized coordinates are. So in this case, I could call it a y1 and a y2. That if I know y1 and y2, I can figure out what y3 is. And if I know the velocity of y1 and y2, then I know what the velocity of y3 is. That's a little easier since we don't have the chord lengths. So if mass 1 is moving up 1 meter per second and mass 2 is moving up 1 meter per second, mass 3 has to be moving down combination. It's got to be double that because it's moving down from the pulley and it's moving down from the mass 2 length of cord. All right, so my generalized coordinates, Q, are y1 and y2. In this case, we'll look at, as we keep getting into dynamics and we get a little bit further, we'll look at more of how computational methods do this when you think of multi-body dynamic solver. Well, not when you think of, but when multi-body dynamic solvers are designed, they're designed with a general principle of just, okay, there's one global coordinate system and then we'll define all of the local coordinate systems as this moves. In this case, I'm using a lot of intuition to figure out like, okay, how many degrees of freedom do I have? Let me choose these wisely so that I can create some equations of motion from them. And this is a nice way of approaching things, but it's not a general approach. Like sometimes sometimes you might end up choosing the wrong generalized coordinate. It's not wrong, but you just end up doing a lot more math as you're trying to solve it. So we have y1, y2 defined. And that means for these 3 moving parts, I still need to know what is y3. So now we can use my constraints that y3 do we want to define some chord lengths or something? In this case, pulleys are nice because it's easier to kind of define relative velocities. So let's look at that. Well, all right, we'll do this. So if we kind of have same things defined, we could say that y1 plus h1, that one is a constant because the distance from the ceiling to the floor is not changing because I move the position of y1. And then if I look at h2 and then this is going to be our y3, h2 plus h3 is y3. And then we have a do I want to call that h4? That's okay. So h4 plus h3 is also a constant. And let's get h2 plus h4 plus y2. So as long as I can write things into like a math equation like this, I can start looking at like derivatives. So if I start taking a derivative and say y1 dot, h1 dot, this is now 0. h2 dot, h3 dot, y3 dot is 0. h4 dot, h3 dot is 0. h2 dot, h4 dot, y2 dot is 0. And this is what I mean by the pulleys. It's helpful to kind of look at velocities. I did it in terms of position, but now I can start looking at like, all right, well, are any of these constant? H2 can change, H1 can, so if H1 and Y1 are both equal opposite, that if Y1 goes up, H1 goes down. H4, H3, those are changing. It's the same as our Y3 term. Okay, cool. So now we can, I was just looking to see if any of these were constant values. If I was taking a derivative of a constant. But now I can start solving for like Y3 in terms of H2 and H3. So I can solve for H2 here. Plug that into this one. And now I have H4 dot plus Y2 dot minus equals 0, and then H4 dot plus H3 dot equals 0. So this could be I could replace this with a positive H4 dot. And let's see if that one makes sense, that I'm saying position 2 is, or really I want to solve for position 3. Because I'm trying to get so if I come back up to my diagram, H4 dot, H4 and H3 are both connected to each other, so if H4 is going up, H3 is coming down. So if this is going up, then this is coming down at the same rate as 2 times H4 dot. I feel like I need an H2 in there, but H2 is that solved in here. I think we're doing okay. Cool. Just double checking things over here. Do it a little differently, but that's okay. Okay, cool. And so I have like a function is a function of, I really feel like there should be, so H4 dot, I feel like H1, Y1 should be in there, right? H1 plus H2 is a constant. Oh, that's what I needed. All right, let's try this again. Sorry about that. Because I'm trying to get rid of those H values and just have it in terms of that one. So I know Y1 dot equals negative H1 dot, which is equal to a positive H2 dot. There we go. So if I have an H2 dot, I can replace it with a Y1. That's what I'm trying to do. And then now I can plug in. So that Y, so H2 dot, I can plug in a Y1 dot. And positive, so this is going to be a Y1 dot. I'm kind of combining these to get rid of, and that H3 and H4, those are equal and opposite. So H2 plus H1 is a constant. H3 plus H4 is a constant. I guess that's not true. H3 and H4 can change even if H. So I think that's where I'm messing up on that one. So this one's not true. But I can say H2, H3, and Y3 are constant. Because one thing that I could do is just move this H2 down to here, and now H3 and H4 both decreased, even though I didn't actually change positions of Y2 and Y3. It's not easy, this stuff, but it is worthwhile. Like, once we get to the right generalized coordinates, then we can plug in, we can start solving for like kinetic energy, potential energy, all of that. H4, H3, and I guess Y2 plus H4 plus H2 is also constant. And that one we have. Let's see if that's enough. Can we solve it from there? So Y1 dot plus H3 dot plus Y3 dot is 0. Y1 dot plus H4 dot plus Y2 dot is 0. So those are equal to each other. So Y1 dot plus Y3 dot equals we can get rid of that one. So H4 and H3, let's see how those, H4, H3, those have got to be connected somehow. To Y1, right? Am I missing anything? I don't want to leave those derivatives in there. I'm trying to get rid of those. You know, I've done this before. I was just checking notes too. So it should be V2 plus that V3 is a combination of both V1 and V2. So if these are both up, this one's down as a negative. h4 minus h3 dot. But those are not connected, not directly connected to y1. h1 plus h2 is a constant. Okay, come back to this if we need to. So now, potential energy is m1 g times y1 plus m2 g times y2 plus m3 g times y3. But we already figured out that y3 has to be related to y2, that it's got to be that h2 and h3 . And then our kinetic energy is going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared. But again, I want to plug in the value of that y2 dot. So for the v terms, these are y1 dot, and this is y2 dot, and here this is my y2 dot plus so taking all those terms and squaring them. Let's see what we got here. Oh, duh. Oh. y1 dot plus y. Do I want to switch it? No, that's all right. So the main thing is that our potential energy is a function of just y1 and y2, and our kinetic energy is only a function of y1 dot and y2 dot. In general, we could have a function, like there might be terms where it depends on both y1 and y1 dot and y2 dot. So general is that it could be a function of y1 So what we're really trying to do with these Lagrange methods is that the velocity is a function of q, and the kinetic energy is a function of Q and Q dot. So we're trying to choose coordinates that work and do that there, so that now when we look at the equations of motion, like the Lagrange, we have dl dq, which is split up into two values, dl dy1, dl dy2, and then we have d dt dl dq dot, which is going to be a d dt dl dy1 and a d dt dl dy2. And in this system, that's all we have is just kinetic and potential energy. We could have like work added somehow, like some other like non-conservative forces, but we haven't really dealt with that yet, and we'll get to it soon. Cool. Okay, so that's what I wanted to introduce, just kind of a not so quick but kind of quick intro to constraints and generalized forces, and see how you think about it. And then I'll come back later and we'll talk more about this problem, about like getting into the equations of motion. But first step is just recognizing how many coordinates you have and what your generalized coordinates would be. All right, thanks for joining, and I'll catch you next time.